Good afternoon, everyone. I'm Bogdan, and I'm with the Department of Ballistics and Weapon Systems at the Royal Military Academy. Today, we are going inside the barrel to explore one of the most fundamental challenges in small caliber weapon systems maintenance: erosion. Our research aims to move beyond simple round counting to a predictive, data-driven assessment. We'll show how we measure erosion with micrometric precision, how we successfully link control lab data to simulated real-world operational wear, and how these measurements help us to predict a barrel's condition long before performance failure. Let's begin. Here is the roadmap of our session. We have 5 main sections designed to take you from the problem to the solution and its validation. We will start by establishing the context, internal ballistics and its role in defense. Then, we will take a deeper dive into understanding barrel erosion and its impact, defining the physical mechanisms that govern a barrel service life. Third, we'll move to the core of our methodology, measuring wear using precision metrology. This covers the tools, their capabilities, and our dual system approach. Fourth, we'll present evidence, comparing the laboratory and simulated operational data to validate our findings and prove the correlation between the two environments. And finally, we'll draw conclusions and outline the next research steps, focusing on operational impact of this work. This study directly supports the core mission of the Internal Ballistics Research Unit, ensuring that the weapons used by the Belgian defense remain reliable, safe, and operationally effective throughout their life cycle. Our work is not theoretical. It provides the scientific evidence that underpins procurement, maintenance, and operational readiness. Internal ballistics governs everything that happens from ignition to projectile exit: how propellant burns, how pressure builds, how the projectile moves, and how the barrel responds to mechanical, thermal, and chemical stress. These factors determine muzzle velocity, consistency, accuracy, barrel life, and the probability of failure during demanding operations. In short, internal ballistics is where the weapon's performance is born. This study strengthens this mission by addressing one of defense's most persistent challenges: barrel wear. Today, the end of life of small caliber barrels is decided mainly through experience and simple gauges, with little correlation to firing history or pressure behavior. Our study replaces this empirical approach with a data-driven scientific method based on most advanced measurement technologies. Our mission is clear and threefold: quantify, compare, and predict erosion in standard 5.56 x 45 mm barrels. We choose this caliber because it's the workhorse of modern militaries, representing the most common system where reliable performance is non-negotiable. To achieve this, we had to compare wear generated under controlled laboratory conditions with wear observed under realistic operational replication. Furthermore, we evaluated two critical measurement tools: the CMM scanning for high accuracy analysis and pin gauges for field level efficiency. Ultimately, the goal is predictive maintenance, replacing guesswork and round counting with objective, physics-based data. We need to know a barrel's exact condition and anticipate its lifespan before performance degrades or, critically, before a safety risk emerges. Barrel erosion is more than just material rubbing off. It's a brutal, complex process. Each shot exposes the bore to some of the most extreme conditions found in any engineered system. We are talking about temperatures above 2000 degrees Celsius, pressures greater than 400 megapascals, and the intense friction as the copper jacket of the projectile engages and deforms into the steel rifling. Add to this the chemical aggressiveness of propellant gases, and you have a perfect storm that removes microscopic layers of steel. This material loss is most noticeable at the forcing cone, the area immediately in front of the chamber. This region receives the full initial blast of gas and heat, while the projectile is still rapidly accelerating. Why does this matter? Erosion alters geometry, which in turn affects internal ballistics, leading to a loss of muzzle velocity, reduced pressure consistency, and ultimately a significant drop in accuracy and precision. Over time, it reduces reliability and introduces potential safety risks, making erosion the definitive factor in a barrel service life. To address this problem, we employ the dual platform methodology to ensure our findings are both precise and realistic. Our first test world was the Ballistic Interchangeable Manometric Cannon, BIMC, in the laboratory. The BIMC provides absolute control over variables. We can isolate pressure curves, control the type of propellant, and maintain a fixed firing rate. This precision allows us to establish the fundamental wear relationship. Our second test world utilized the FN-SCAR barrel under operational replication. Here, we introduced real-world simulated conditions, varied firing cycles mimicking combat usage, actual temperature spikes and cooling periods, and the inevitable effects of fouling and carbon buildup. By comparing the BIMC's controlled precision with the FN-SCAR's operational realism, we could effectively validate whether laboratory-derived data accurately predicts field-induced wear. Quantifying this invisible, gradual process of erosion requires sophisticated tools. We needed methods that could map the wear for research purposes, and methods that could be used quickly and reliably by an armorer in the field. This led us to our dual metrology approach. Our philosophy was simple: synergy. We required one tool for micrometric, research-grade precision, and another for robust field-level efficiency. The first tool is the Coordinate Measuring Machine, or CMM. This provides a high-resolution 3D map of the barrel's internal geometry. It is our absolute ground truth for volumetric wear. The second tool is the simple, yet highly reliable steel pin gauge. This is used for quick, reliable diameter checks directly in the field. The crucial point of our methodology is using the CMM data to validate and calibrate the pin gauge trends. We establish the link between the two, providing a traceable and dependable method for maintenance personnel. The CMM scanning process using a sophisticated seismic Cura provides high-precision geometry mapping. This machine uses contact probing to take millions of data points from the bore. Critically, we perform circular scans every 125 micrometers along the forcing cone. That resolution is necessary because erosion isn't uniform. This can generate detailed 3D wear profiles and dimensional maps. The data then allows us to calculate volumetric material loss. This is the most objective, physics-based metric we have for tracking wear. The CMM effectively transforms otherwise invisible wear into quantifiable volume loss, clearly exposing the severity and localization of the erosion zones. In contrast to the CMM, pin gauges represent the practical, fast, and reliable side of our metrology. These are essentially hardened steel rods of precise known diameters used for bore diameter checks. They detect wear in small incremental steps, often down to the tenth of a millimeter or less. They are portable, cost-effective, and require minimal training, making them perfect for routine maintenance level inspections. The entire procedure, inserting the pin and measuring the depth at which it sits, takes less than 2 minutes. This rapid data acquisition is the key to incorporating our research findings into a workable field maintenance schedule. This section is the moment of truth. Our research hinges on a core hypothesis. Does controlled wear generated in the lab truly reflect what happens to a soldier's rifle in the field? By comparing the results from the BIMC and the FN-SCAR, we can validate our methodology. The CMM gives us the most granular evidence. It reveals subtle yet critical aspects of bore evolution, such as initial smoothing of the rifling lands and the progressive widening of the bore. Look at these cross-sections. You can see how the diameter increases, not uniformly, but preferentially at the point of maximum thermal stress, right at the beginning of the rifling. This visualization confirms where the wear mechanism is active and provides us with the precise geometry we needed to build accurate predictive models. It turns the invisible erosion process into a clear, measurable continuum. Here we present the core data from our control laboratory findings using the BIMC. We observed a clear and progressive increase in barrel diameter that is directly proportional to the shot count. The forcing cone was consistently the zone of highest wear. Crucially, our analysis allowed us to pinpoint when a significant change occurred. We detected a measurable inflection point in the rate of volumetric loss. This volumetric evolution confirms that the wear process is steady and, most importantly, predictable through physical measurements. This data is the foundation of our predictive maintenance model. Moving to the operational data from the FN SCAR, the pin gauge measurements, which represent simulated real-world weapon behavior, tell an extremely compelling story. The erosion pattern closely reflects what we observe in control laboratory testing. The overall trend remained the same, steady wear centered on the forcing cone. However, we also see the effect of operational noise. Factors like dust, differences in firing cadence, and carbon buildup introduce additional variability. Despite this expected variability, the trendline confirms that the control laboratory conditions are a powerful proxy for simulated real-world wear, effectively validating the predictive reliability of our BIMC testing setup. When we integrate the CMM and pin gauge data, we confirm the same story inside the barrel for both lab and field trials. The CMM provides the high-fidelity detail, the why the barrel is wearing. The pin gauge confirms the macro trend, the what is happening to the bore diameter. This strong correlation validates the predictability of the laboratory setup and allows for effective cross-validation. This is the key. We can use the CMM scanning to generate calibration tables for the simple and fieldable pin gauges, thereby translating the research-grade accuracy into maintenance practicality. The most significant result for weapon maintenance is presented here. By quantifying erosion as volumetric material loss, we established that the volume increase is directly proportional to the number of rounds fired, showing a nearly linear wear. This linearity means that the volume loss is reliable, physics-based metric for barrel's lifespan estimation. We can confidently move beyond simple shot counting, which ignores firing conditions, to a true wear-based assessment that directly supports predictive modeling and maintenance scheduling. This model allows us to project the barrel's remaining safe life based on its current measured state of erosion. We have successfully quantified barrel erosion and established a predictive relationship. Let's summarize the key takeaways and discuss how this work moves forward. Our research provides 4 critical findings. The forcing cone is the critical wear region, making it the target for all future inspection and material science efforts. Erosion can be tracked and predicted through precision metrology, moving barrel maintenance from reactive to proactive. We have successfully paired high-tech with low-tech. CMM provides the high-accuracy analysis necessary for research, while pin gauges deliver the field efficiency required for operations. Most importantly, laboratory tests accurately reflect operational wear patterns, giving us the confidence to use control testing to model future weapon performance. The impact of this work is significant for the end user. This approach enables proactive barrel replacement before failure occurs, which is a dramatic shift in maintenance philosophy. It directly enhances weapon reliability, safety, and overall mission readiness by anticipating degradation rather than reacting to a catastrophic failure. At the same time, it reduces maintenance costs and operational downtime by allowing for efficient scheduling of barrel replacement. We can get the most life out of every barrel while ensuring soldier safety. We are strengthening the link between precision metrology and weapon performance, turning measurement into a key element of operational readiness. Looking ahead, we have 3 steps to further refine this predictive capability. We will enhance CMM scanning strategies to enable even more detailed 3D volume modeling of the erosion topography, which will refine our wear calculations. We plan to refine laboratory firing cycles to more accurately replicate the thermal and mechanical stress profiles experienced in specific operational theaters. Finally, by integrating all laboratory and field data, we aim to develop a hybrid predictive simulation that bridge control testing with simulated real-world behavior using advanced data analytics. This study was carried out within the Department of Ballistics and Weapons Systems at the Royal and Military Academy in Brussels. I extend my sincere appreciation to all my colleagues for their support, collaboration, and expertise throughout this complex project. And I thank the Royal and Military Academy for providing the cutting-edge facilities and resources that made this work possible. To conclude, erosion is not random. It is measurable, predictable, and manageable. By looking inside the barrel with precision metrology, we transfer maintenance into prediction. Thank you for your attention.